because every time the values change, the whole hash value changes, because now it's treating that as a total new image. Okay, and just imagine that will become even more tougher if we talk about the different manipulations that we just talked about that people can do on top of encrypted channels, like applying a filter, resizing, compression, and so on, right? So it was super challenging, and the algorithm developed by Hani Farid was not working now, right? So I was fortunate enough to work with Professor Hani Farid during my postdoc, and that was the forensic project that I started uh, working on, my first forensic project, and it was super challenging. So I try to put out what are the different things that we have to focus on when I'm devising an algorithm, right? So the first thing is that I should have a unique fingerprint for every image, right? And encryption, it introduces randomness, right? A becomes Z, A becomes K. So it's changing every time. Then there is a class of encryption that is a convergent encryption. As the name says, converge, it uses the content of the image and gives you a fixed value based on the content, right? It could be a possible solution, so I listed it out. But again, for encryption, the content is changing, so it's not working. Then, if we have to work on top of encrypted channels, we are not looking at the original content, right? And it is super time taking, right? So if you're devising something to work in practical applications, for instance, people will not wait for more than few nanoseconds to upload a photograph, right? If that happens, we'll be very annoyed. What is this website doing? And we will not use that website. We'll move on to some other platform, right? So that was another challenge. Time factor is very crucial, right? So I listed out all the possible things that I have to focus on. And then the most important thing was I should have a very low false alarm rate. For instance, if somebody is sharing the photograph of the newly born kid, let's say the father is working overseas or the mother is working overseas and they have a new arrival in the family and they're sharing the photograph, that can't be flagged as a child abuse material, right? So it's really, really important to have a very low false alarm rate, right? When I'm talking about very low, it is 1 in a 10 million. That scale I'm talking about, right? Because it's easy. It's if I have to, like, if a court has to evaluate, is it fine to charge some innocent person as guilty or to leave some criminals, it would always choose to leave some criminals rather than charging an innocent person as guilty, right? Because that's not fine, right? So that is what is meant by very low false alarm rate, right? So those are the challenges. Now I was actually breaking my head a lot, and I have to really work hard to try to get to a solution. But luckily, I cracked this. And what I used was one class of homomorphic encryption, right? So, as the name suggests, homo means you can work on top of encrypted pixels without seeing it and still able to process it, right? And when you decrypt it, you will see the same value, right? For instance, if A is becoming Z and B is becoming K, you can still process Z and K without seeing the original values. And if you decrypt it, you'll get the processed version, right? So that was something that I thought could work. But then again, back then, so I came with the solution around 2018, 2019, I guess 2019, because that's what I got a research paper published in one of the A-star conferences. Uh, so I tried again, like the important crucial point was I have to look out for something really fast because if you're working for something real, working in actual rather than just some solution or a research paper, those are two different things, right? So I have to look out for some simple properties that will work really fast and and takes just few nanoseconds, right? So I went for a partial homomorphic encryption rather than a fully homomorphic encryption. And the difference is when I go for a partial, it allows only certain computations, right? Very basic ones. So it allows the addition and the scalar multiplication, right? That what does that mean? Addition, if I add two numbers, I'll get the same value if I add the same two numbers by encrypting it and decrypt it, right? That's what property one says. And property two, it's multiplying a number by some scalar value, and if I decrypt it, I'll get the same value, right? So one can argue that second property is not a new property, it's adding the same number s times. I agree, right? So in total, I'm just left with just one property, right? Able to add the numbers without actually seeing the numbers, right? Now, if I'm talking about developing a very complicated algorithm with a very low false alarm rate and very accurate and with just one property that I can just do the additions of the number, that was super challenging, right? So I was actually knocking my head out. And one day I had my eureka moment after a lot of failures, right? I'll tell you what the solution I came up with. So here you see a histogram, right? So histogram is basically showing how many, it's a count of how many pixels falls into different ranges, right? So I'll talk about a very simple case. Let's consider a grayscale image, right? A simple 8-bit grayscale image. So if I say 8-bit, that means the pixel value ranges from 0 to 255, right? And here I have tried to make it very simple. The whole range of 0 to 255, let's say we chuck it out into four buckets, right? So equal four buckets. So 0 to 64, then 64 to 128, 120 onwards up to 192, and 192 onwards to 255, right? So you have four buckets. You pick up pixel and see which bucket it falls, right? And also on the y-axis, you see there are different derivative values, right? Derivatives, y derivatives, because for images, the most prominent property is the edges, right? And those edges, they are computed. Edges is nothing but a variation of the pixel values, right? That's why derivative. Like people who are coming from the basic maths background, or you have maths in your schooling, you know what the derivative means, right? There is a change, there is a variation, and you calculate that with 2 points, and you see the tangent of the slope, and that's what the derivative is, right? The variation in the pixel values. So on the y-axis, that's what you see is plotted. So the numbers inside every cell is actually a count of the pixels that is satisfying both the criteria. It is falling into that intensity color range. For instance, if I count a pixel is falling into the first cell, it should have a value in range of 0 to 64, and it should have a spatial derivative in x direction because I'm talking about a 2D image greater than equal to 0, right? If I have that, I'll count that, okay, this pixel belongs there. Likewise for the other cells, right? So all the numbers that you see inside these cells are actually a count of the pixels that are satisfying both the criterias, right? Property one and property two, right? And it is just a simple histogram. Why I went for just accounting, not the actual values? Because, as I said, on encryption, every time the content changes, right? But the count will remain the same. That's what I miss you. That's what I exploited. That the count will remain same even though the content changes, right? So it's very basic, simple logic. But when we are actually developing complex solutions, we often forget the simple solutions, right? So that's the simple thing that I used. I'll skip this slide and happy to share it if somebody is more into technical details. Here on this slide, I'm just explaining what are the basic mathematical operations and how those will be transformed in the encrypted domain, the same computations using the homomorphic properties. So I'll skip this at the point but happy to answer your questions at the end of the talk. Now let's look what I got from this algorithm. So I validated it on a data set of around 15,000 unique images. What I did, I have two class. One where I have all the images as different, and the other class is where I took an image and made around 7,500 variations of each image, like applying different filters, applying different resizing, applying different noises, all the different distortions of the same image, right? So I have two different classes. Now my algorithm should tell me whether this, if I pick an image, it's the variation of the same image or it's a total different image, right? Because that's what I want. The thing is, if it's a child abuse, I should be able to flag it that it is a child abuse. If it's not a child abuse, it should say, no, no, it's not a child abuse. It's a total different image, right? So let's look at this ROC curve. So ROC curve, those who have indulged into some kind of research activities, it's one of the most common metric that is used, but I'll still explain what are the axes here, right? So the y-axis is the accuracy. Accuracy means the true positive. How many cases are really true? If I'm saying it's a child abuse, is it really a child abuse? True positive, right? And on the y-axis is the distance. Distance means I'm taking two images and seeing how close they are using very simple distance measures. Like I can use a Euclidean distance, I can use Manhattan distance, I can use Hamming distance, anything, right? So I went to a very simple distance, L1 norm, and I computed the distance between the two images, right? Let's see the crossover point. Now the crossover point is having a 99.1 accuracy. That doesn't seem like very accurate, right? But what does that mean? This crossover point, 99.1, is when I am fixing my false positive at 1%, right? So that means only 1% of the cases are wrong. But then I said that it should be a case of 1 into 10 million, right? Then let's go to the other cells. The accuracy drops when I go for 0.1%, right? It drops a little. So from 99.1, it comes down to 98.3. Not too bad, right? Then I experiment a little more. 0.01%, it drops. Even more, 0.001%, it drops. And 0.0001%, right? That means 1 in a 10 million. The accuracy still holds to 93.94%, right? Good enough. So if I'm talking about having a false alarm rate of 1 in a 10 million, and still I'm having my accuracy at 93.94%, that's a great news, right? So I was actually really shocked when I got this accuracy. And when I showed that to Honey, he was also not believing it. But then we double checked it, run the experiment 2, 3 times, but still that is what I got, right? So what I'm trying to say here, sometimes the problems may seem super challenging, but uh, what I got from working with these top people, the solution lies in very basic steps, right? So we all know, uh, like Corman, who I'm talking about Corman, who's the the famous algorithms and data structures writer. He was also a faculty at Dartmouth, right? And I had a chance to meet him several times while during lunch or Friday evenings where we have faculty and research scholars talking around. And what I got, the solution really lies in very basic and simple things. It's there on the table, but everybody is looking for more complex solutions, and that's why we overlook the simple solutions, right? So uh, this is what I'm trying to emphasize here. And then we checked the robustness of this with different, noises, with different JPEG compression, with different scaling or resizing of the image, and the algorithm was working fine, right? If you can see, the algorithm is still holding more than 95% for the gamma correction, for the noise still, like it's a flattening towards as we increase the noise. Same goes for the JPEG quality and the scale. So we checked a couple of manipulations and saw how the algorithm was behaving or reacting to it. So it was pretty decent. It was above 95% for all those manipulations. Later, I extended this idea after my postdoc. I extended this idea to video hashing. And video hashing is even more challenging because we know, first of all, video involves a lot of processing. In comparing whether two videos are same, the videos could be a different length. So there is no defined metric for it, right? So I used my basic knowledge of algorithms, and I used a longest common substring to see whether a big video is having a matching video snippet, right? So again, the foundation was very basic, very simple, and it gave a very good algorithm. I'll again not go into the details. I'll skip that here. And I extended that further into my first position, like when I joined as a faculty. I developed this algorithm further for chalking out the forgery in the documents, like the government documents. If there is any manipulation of the seals or the signatures, if there is manipulation in the documents. And this solution was working really well, and I was fortunate to work on a government project and still being used now. I have done a couple of projects on the forensic side of things. So when we click cameras, every camera has a unique fingerprint, right? Even if you take the same camera, the same make, same model number, still if you click photographs, it will have a different fingerprint. That is called the fingerprint of the camera or that particular device, right? And we use that photo response non-uniformity pattern, PRNU, in the forensic field for investigations. We try to correlate on the crime scene. If we find a photograph or we find a camera, we try to correlate it by downloading images from the social handle of the suspects or the culprits and try to see who could be the potential one, right? So that was another idea. Right now at UQ, I am focused on, again, a project. Nowadays, we have a lot of misinformation slash disinformation, right? So the difference between mis and disinformation is misinformation could be right or wrong, and it's not intended to falsify the people, but disinformation has a targeted audience where the whole point of propagating that information is to deceive the people, right? So it's super challenging to combat disinformation compared to misinformation, right? So that is something right now very crucial in Australia, and that's one of the projects I'm really focused on at the moment. You can see, like, just an example, if you look at these two images, of course, the bottom one is a falsified image where the president is actually put in front of, and it looks like he's giving a speech, whereas there was no president in the original image. It could change the perception of the people when it is being propagated on the social media, right? Uh, it is also, I also did some work for finding the manipulation in the satellite images because satellite images are very costly, they're very minute. If there are manipulations, it can, because everybody is using the satellite images for doing a lot of stuff, right? So if somebody is forging there, it is a thing of national importance. With this, I'll stop my talk and happy to answer a few questions from our audience. Samantha, can you help
Can
me
you
if there
hear
are some
us?
questions? Yeah, I can hear.
Okay. So thank you for your interesting talk. Actually, the figures and the manipulations, how they are supporting for the crime, it looks really interesting. Audience, you have any questions? I may have one question like, is there any new thing you have done for the AI related manipulation in the image? Like that's really challenging for human eye as well. Like we also couldn't like distinguish. Okay, this is from the AI. This is from the human. Are there any
Oh yeah.
new researches going related to this?
Oh yeah, yeah, yeah. So that's what like deepfakes. You're talking about deepfakes, and deepfakes are so subtle and sophisticated right now at the moment that it's really tough to identify with our human eyes, right? Even the AI algorithms can't chalk it out, right? I'm doing a lot of work on deepfakes as well. I'm collaborating with Cairo, which is a government research agency on developing solution on deepfakes as well. And we are trying to develop that solution for end users who are not technical, like not coming from a technical background, so that the algorithm will tell you which portions are deepfakes and for what reason, right? And I'm using these chat GPT and other LLMs to help people to put query and get their curiosity satisfied.
Exactly. Yes. Yeah. Thank you for that. So I hand over the session to Sensor Lab to do the water plan.
Good afternoon, everyone. On behalf of the IEEE Women in Engineering Student Branch Affinity Group of the University of Jaffna, it is my great pleasure to extend our heartfelt gratitude to our esteemed speaker, Dr. Priyanka Singh, for delivering such an informative session on cyber forensic in celebration of IEEE Women in Engineering Day 2025. We truly appreciate you taking the time to share your expertise with us today. Please accept the virtual token of appreciation as a small gesture of our sincere gratitude.
Thank you so much. Pleasure.
A special thank you for all the participants who joined with us today. Before we conclude, we kindly ask you to take a moment to fill the feedback form. Thank you once again.
Thank you, everybody. Thank you for the opportunity. Okay, Samantha, can I leave now if there are no queries from the students?
Hello, Priyanka.
Yeah, yeah.
Yeah. Do you have any questions? Uh, no, they don't have at the moment. But if they have anything, I will send an email to you surely. They may,
Okay,
yeah,
okay.
they may ask to that having shy to ask, but I will let you know. Thank you
Yeah, yeah,
for your
sure.
time. Thank you for your time to share your thoughts with us. Thank you.
Yeah, it was great connecting. Yeah, all the
Thank you.
best.
All the best. Thank you. Bye.
Yeah, yeah, bye-bye.